Okay, so what are the limits? That's one of the first things you learn in calculus proper. By the way, so what is calculus? Some people just say calculus is the study of derivatives and integrals, and that's fairly good. But remember, both the integral and the derivative are defined in terms of what? Yeah, limits, okay? And the continuity, if you remember, is defined in terms of limits for these kinds of functions we are studying. So really, it's all about limits, okay? So typically, the calculus is defined as a study or the mathematical branch involving limits, continuity, derivatives, and integrals of functions. And so limits, of course, is a foundational idea of calculus. And so you really need to understand this, even though we are not going to put a lot of emphasis. I mean, theoretically, this is the fundamental idea that developed later into a rigorous form of calculus. All right, so we have the function. This is a function from R to R, right? And then this is a function fx. And as x approaches a from both sides, if the value of the function fx approaches a particular point, okay, this is called L. Let's just call this L. And so that's a definition. And in fact, you probably learned this as a quote unquote definition because this is not a proper definition acceptable by the mathematical community for limits. But we all sort of understand limits this way, even though we don't define this. I mean, this is not rigorous enough, okay? So we say that the limit of the function as x approaches a is equal to L if fx approaches L as x approaches a from both sides. All right, so the idea is, you know, if as x gets closer and closer, that's a great word, but a term, by the way, closer, closer, and closer. Okay. In fact, there's a, by the way, calculus is in a branch of mathematics called mathematical analysis. So when you study analysis, especially real analysis, that's calculus with real numbers. Complex analysis is calculus with complex numbers. What else? Hard calculus means calculus that's really hard, okay? Whether it's real or complex. But the whole idea is that you let numbers get closer and closer to some real number or some complex number, all right? So the closer and closer idea really captures the critical, crucial spirit of this thing called calculus. Okay? In fact, there's a famous book on calculus called Closer and Closer. That's a great, great title. All right, this is it. But here's a problem, okay? This is not rigorous enough. And in particular, we don't really care what happens. And in fact, for most limits that are important to us, the value of the function doesn't exist at a, okay? So even if a has a little hole here, let's say this is your, you know, line. Even if there's a hole here and maybe the hole is filled over here, you know, f of a was way up here, okay? But the limit is still L, even if there's a hole here. So one key element that I didn't write on purpose for this quote unquote definition is that without x being equal to or exactly equal to a, without a, x equal to a, right? So we can let x get closer and closer and closer to a, but we never let x be exactly equal to a, all right? So that's the definition. Now I think I'm going too much into this because for this particular section, you don't need to know all the definitions and everything. So if you don't understand what I'm about to write fully, that's okay. But the whole idea of this is not rigorous enough for proofs, right? Which are required to prove a bunch of things, theorems regarding calculus and limits and so on. The definition that much later mathematicians came up with, much later than Leibniz and Newton, is this definition of a limit. We say the limit of f of x as x approaches a is equal to L if for each epsilon, and what we do is we let epsilon be a small deviation, a small number away from this L. For each epsilon, which is a small number greater than 0, there exists a delta. A delta is over here, okay? delta still greater than 0, such that whenever x and a, this is the absolute value of x and x minus a, which is the difference between x and a, the distance between x and a, you know, if this is x here, if this is less than this epsilon, if this is less than this epsilon, which is meaning that x is within the epsilon units away from the point A. Okay, so x is, whenever x is really, really close to A, mainly between a minus delta and a plus delta, if x is within this small open interval about A, then f of x will not deviate from f of a, which is your L. Oh, so this should be L. Remember, f of a, we don't care what that is. The difference between the limit and f of x is within epsilon. So if somebody gives you a very small epsilon, 0.0001, for instance, can you find your delta so that as long as x is within delta units away from a, then f of x is within the epsilon distance of L, okay? If that's the case, if you can find the delta for each epsilon that would satisfy this, we then say the limit of f at A is equal to L. So that catches things like this away from here, and it solves all the problems. This definition is an extremely important one of the most important ones in calculus, in mathematics. And then it gives, I guess, foundations of other theorems you can prove. Now, I deliberately left something here. I don't know if you noticed here. I said, remember, without x being equal to a, I have to also stipulate that. And to do that, I just put 0, greater than. Okay, so x minus a, the absolute value of x minus a can be less than delta. It has to be strictly greater than 0, which just means, this just means that x can't be equal to a. If x is equal to a, we don't care what happens at that point. And so that's the definition of the limit, all right? And then you notice here, if f is continuous, this is what you learned in calculus 1. If x is continuous at a, then then the limit of f as x approaches a, it turns out to be exactly the value of the function, because continuity means that you don't have any jump like this, or a gap, or you know, anything else as ugly or asymptotes, or hole like that. And so without holes and gaps and asymptote, this will be true. Okay, and in fact, this is a little cheating because we haven't defined what continuity is. And it's also cheating because we define continuity based on the limit being equal to the value of the function. But anyway, I don't want to go into all the details. This is the important part, right? Most of the functions we'll be dealing with in calculus 3 will be continuous functions. So in order to find the limit, all you have to do is to plug in the number whenever you can, right? Let me go ahead and write down this. Yeah. So now for a function which is from R to R3, I mean, this is the same thing for R2. So what I'm talking about is something like this: xt, yt, zt. Notice here, xt, yt, zt, these are all real valued functions, the kind we studied up here, okay? So we will define the limit. This is if f is defined this way, then the limit of f t as t approaches a particular point A is equal to the limit of xt as t approaches A, limit of yt as t approaches B. It doesn't approach B, there is no such thing. A, and then the limit of zt as t approaches A. I'm not saying anything surprising. Oh, by the way, many times limits may not exist, so if it exists. That's sort of a disclaimer. That's number one, okay? Number two, we say f of t is continuous at t is equal to a if the limit of f of t, limit of f as t approaches a is exactly f of a. All right, and so that we use that as a definition of continuity, just as we do in calculus 1, even though before calculus, we said f is continuous, if there's no gap or asymptote or hole, which is exactly what this is saying. All right. Any questions here? Maybe number 3. We say f of t the domain of f is negative infinity to positive infinity, except where f of t cannot be defined. Now, just so you know, okay, we've only had a few cases in here. So for instance, what can you not have if you have a denominator? Okay, 1 over x. Okay, you know x can be 0, right? So avoid the 0 denominator. If any x or t will give you a 0 denominator, then you should avoid that. That the value of t should be taken out of the domain. And this could happen at things like the tangent function or the reciprocal function. Denominator. Okay. You should also avoid the negative numbers in the natural log or log, the common logarithm, or any sort of a logarithm. You should also avoid you should also avoid 0 because ln of 0 is undefined. Okay. You should also avoid negative number inside of or under the square root sign. Okay. And really, this is about it. I mean, technically, there may be a few more exceptions that you have to think about, but this domain, which is not specified, but is sort of implied or understood, is called the natural domain. So the natural domain is a set of all values t so that each component x, y, z is defined at that point t. If any of these is not defined, then we have to remove those points t from out of the from the domain. Okay, so here's an example. We are not going to talk about the derivatives yet. That will be coming in section 2. But let's say, one more thing. I should have said this earlier. Okay, because in this situation, f of t, this is, let's see, f goes from r to r2 or r3. And these are called vectors, right? I mean, these are 2 or 3 dimensional spaces, but we consider them to be the set of vectors whose terminal points are those points in R2 and R3. So we call them vector value functions. So from now on, I will probably not be using this f of t. F stands for a function, but for whatever the reason, people like to use this lowercase r. So r with an arrow to show that this is a vector valued function. And so this is a notation we'll be using for most of our functions. I already used it on the first half of this lecture when we talked about r1 of t as cosine and sine and r2 of t and so on. Okay, so from now on, we'll just use r, and that's just a standard convention. I didn't choose to do that. And you can keep writing f of t, but you might as well learn to be like everybody else. Right? R of t is equal to t squared 1 over the square root of t. This is just an example. Right? And let's do this. T minus, what do you want? T minus 3. Okay, so find the natural domain. The question will typically say find the domain. Okay, and that means find the natural domain. right? The idea is we include everybody. Of course, we do. We're Californians. We include everybody. We don't discriminate, or do we? Well, sometimes it's just impossible to let people in. Like if t is 0 and t shows up at the door and says, "Look, I'd like to be evaluated," literally. Okay, if t is 0, you can't evaluate it because 1 over square root of 0 does not exist. You just say, well, I can't. All right, so the point is we have to make sure that every part makes sense. For this one, t, because the square root of t is in here, t has to be greater than or equal to 0. Okay, that's only because the square root of t will not allow negative number to be inside of the radical if without allowing complex numbers. We are still working on the real number system. But also if t is equal to 0, you have 1 over 0, right? So that means t can't be equal to 0. So the second component, which is the y component, says t has to be positive. Okay, t has to be greater than or equal to 0, but by virtue of being in the denominator, t cannot be equal to 0. So this one here says t minus 3 has to be a positive number. See, after the log, or any log, especially ln, you cannot have 0 or negative number. It has to be a strictly positive number, which means t has to be greater than or, greater than or equal to 3. And both of these have to be together. T has to be greater than 0 and greater than 3, right? So it has to be greater than that and also has to be greater than that. Both of them have to be equal to true. And therefore the answer is x has to be greater than 3. That is your domain, which also, t, which also tells you can write this in terms like this, 3 to infinity. Or 3 greater than t greater than infinity. That either of these will be okay, but that's the answer to the question. All right, I want to do a couple of examples. Maybe I'll pause here at the moment at this point, and I'll do maybe 3 more problems similar to the ones you would experience in on your homework.